Alright, we're going to talk a little bit here. We're getting close to talking again about vapor pressure because vapor pressure is going to be a big component of our colligative property, really the remainder of this chapter. Just quickly, I want you to pull up in your book, turn to page 505. You guys hear all these vitamins before, but you know, there's a structure of a couple of vitamins here, vitamin A and vitamin C. You need to see these structures. A lot of times we deal with, you know, your very basic Lewis structures, your very basic structures, but there's quite a bit of things that are a lot bigger than our carbon tetrachloride, you know what I mean? Okay, so if you look at that, just looking at vitamin A structure versus vitamin C structure, could you tell me anything about whether they're polar or non-polar?
Vitamin A looks pretty polar.
Why is that?
Well, it has a hydroxide on one end.
Sorry?
It doesn't look very balanced, I guess. I don't know.
Sorry? Anybody else want to add anything? Change
It
anything?
does say it's non-polar, though.
Yeah, it's definitely non-polar. Why?
On the description says.
Look at all of those bonds. What bonds are they between? Except for the very last one on the far
Carbon
right.
and hydrogen.
Carbon and hydrogen have such similar electronegativities, that's virtually non-polar. Okay? The end of it has one little small polar region. That's it. Otherwise, the whole entire molecule is virtually non-polar. Okay? And in your vitamin C, you have a whole bunch of significant differences in electronegativities, which is going to create your polarity. Okay? This has a significant impact on how it acts. The structure that it has is going to impact how it acts. Okay? When you're sick, do you guys just down orange juice left and right?
I love orange juice, though.
Okay.
Yes.
But how many times have you heard people say, you know, drink a whole bunch of orange juice?
Yes, and I would probably die, but
Okay, yes.
yes.
You heard that, right? Did you know that there's only so much vitamin C your body can take in a day? So essentially, you drink, what, a glass and you're good? And that's all you can pretty much absorb, and the rest you just pee out. And the reason why is because it's polar, and it's attracted to the water in your body, and so therefore only a small amount of it can absorb, and the rest just washes away. Okay?
That's why the ones that you can get sickness from too much vitamins.
Yep. Vitamin A is the one that can be dissolved into your fat, which is non-polar. So your body can store it away for later use, and that's why they say if you have too much of your fat-soluble vitamins, it actually can kill you because you don't want to be storing away. It's not healthy for you to, you know, put all that vitamin into your fat. I don't know why exactly. It's been a while since I studied that. But
So, but if you have more fat, does that mean you can store more vitamins?
probably, I don't know.
Well, if you're gonna have to be a walking health machine, it's like all the vitamins all the time.
Where do you get them from?
Well, that's a great question. I don't know enough about it. I think anything that's synthetic is probably not very as productively good for you as getting it from your, you know, your daily stuff or your, you know, your eating or your sunlight or whatever. But I'm sure there's some value, but I don't think it's. I think they're making their money's worth on you. Depends on the situation. I know that my wife has been low on iron, so she's taken iron pills, and it's helped with a couple things. But
Yeah.
I don't want to say they're completely not useful, but I don't think they're probably as useful as.
Is melatonin stuff that makes you sleepy?
Yes.
Yeah, I think you can take that.
Yeah, melatonin.
Yeah, yeah. No, I'm not knocking on that stuff. I'm just saying my general belief is
Well,
the synthetic medicine.
Artificially taking melatonin can actually make your body, make a heartbeat fall asleep without medicine, though, because your body relies on not having to produce it itself. It's just chemical your brain produces.
You're essentially tricking your brain,
Yeah.
which is what most drugs
Well, like
do.
Tylenol. Tylenol too. Like you take
Yeah.
more and more of it, your body kind of goes like, no, it hurts for a reason.
Yeah.
It's like overriding the
Yep.
resistance thing.
Which it's nice that our body can like be dying and not know it, but at the same time it's not.
Yeah.
Like how many times do people realize they have stage 4 cancer just out of the blue? Well, does that mean stage 1 cancer doesn't do anything? So,
That sounds so bad. Just like wake up, go to the doctor.
that happens to
Yeah, I know. You go,
thousands of
I
people.
know, you go to the doctor for stomachache. Like, oh, you're dying. Sorry. That's kind of sad.
Most of the time, you know, the symptoms of those are so minor early on that people don't go to the doctor. I should go to the doctor for my fingers. I think I got cancer on my finger. I showed you that, didn't I? Skin cancer. Got like a bone growth right here. It hurts. Anyways, pressure effects. Let's see here. I want you guys to turn to page 507 here. So we're going to talk today kind of about the effects that things have on solubility. We'll talk about pressure and temperature today. Some of them are pretty common sense. Others, you know, might be like, oh, I didn't know that. First off, it says that pressure has little effect on the solubility of liquids or solids. Does that surprise you? Does that make sense? And can you explain why that would make sense or not make sense?
They don't compress.
Yeah, they don't compress, so pressurizing it isn't going to cause it to dissolve anymore. Okay? So that should, for the most part, make some good sense. So it really doesn't have any significant effect. However, it does significantly change the solubility of a gas. High pressure causes gas to dissolve more. Why?
The particles are closer together.
Okay, you're compressing it. You're taking these high energy gas molecules and giving them less volume to be in. Okay, so if you look at the visual at the top of 507, okay, we have talked about vapor pressure. What is vapor pressure?
It's gas particles released from the surface of a liquid.
Okay, and those gas particles exert a what? Pressure. Okay, so if you look at the visual A there, you can kind of see that you've got as many red arrows as green arrows. What is that signifying? Yeah, it's at equilibrium. 4 red arrows, 4 green arrows. That means that a water molecule, or whatever that solution's molecules are, is evaporating as quickly as the gas particles are redissolving. Right? When you increase the pressure, what that does is reduce your volume and cause more gas particles to redissolve. So you start to see the vapor pressure start to go down as more gas particles redissolve in solution. And eventually, it reaches equilibrium again after more gas has dissolved back into the liquid. What is the most common thing that you probably experience on a day-to-day basis of gas being dissolved more under high pressure situations? Soda. Right? You pop off your soda, top or whatever, and you hear immediately you hear the sound of the compressed gas. Happiness. Yeah, that's true. Okay. And over a period of time, it doesn't take very long, and you can definitely tell the difference between a carbonated beverage and a non-carbonated beverage after a period of time.
McDonald's soda fountain, and they're always flat.
McDonald's flight.
Yeah.
Just right.
Because they don't put enough water in the syrup, so it's too concentrated. But some sodas, they're always flat at McDonald's. At least it's called the Hill one. It's kind of cracking.
Okay, so Henry's law states that the amount of gas dissolved in a solution is directly proportional to the pressure above it. Okay, so the more pressure, the more it dissolves, and it's a nice linear relationship, thankfully. So let's take this idea of our soft drink and why you know, it's carbonated right when you start, and then after a period of time, it's not as carbonated. Okay, so you got a certain soft drink, okay, at a certain temperature, and the pressure is 5 atmospheres in the first situation. Okay, then you open it, expose it to the atmosphere, and the partial pressure of your CO2 dramatically goes down. Calculate the equilibrium concentrations of CO2 in the soda before and after you have opened the bottle. The math here isn't too overly difficult, as you could probably imagine. So C closed and C open. Whatever you want if you don't prefer that. Okay, they both have the same constant. Where is that constant? Times 10 to the negative second. I'm not going to write those units in for the sake of time. Okay, what is the pressure in the closed situation? Kind of a lot of words up there, I realize, that for a really quite simple problem.
Why VTM?
Yeah, it's really not hard for one words. Now, as you look at this, you can see how the atmospheres, I'm going to cancel out with the atmospheres, leaving you with moles per liter, which is going to tell you how much of this you're going to have in your liquid, the concentration of your gas dissolved in it. Somebody plug that in your calculator.
.031. That times 5. What did I do wrong? Oh, I didn't do times 5. I did times 1.
That would be,
That would be.
I was going to say, that looks oddly familiar.
1 by 5. I don't know why I times 1 instead of times. It's like, oh.
Okay? Now, you might think, well, that's not that much dissolved. Well, you know, you don't get so much gas to dissolve in a solution. And why could you only get so much gas to dissolve in a solution? Why is it hard to get gas to dissolve in solution?
It's high energy.
Yeah, it's high energy, and it wants to break out of solution. It has enough energy to break away from the forces that water is going to have, or attraction that water has to it. Okay, and the other number is even quite a bit lower here. Yeah. Temperature effects. What is typical common sense tell you from your typical experience that temperature, the effect temperature has in dissolving things?
For
Solids and liquids.
An increase in temperature dissolves faster.
Usually, yep. There are situations where it's not the case. Okay, and for gases, it does what when you raise the temperature? What do you think? What would you think? Without, you know, looking directly at what it says. Yeah, why? Why would an increase in temperature make the gas less likely to dissolve or more likely to come out of solution? Yeah, you already have a gas that has a lot of energy and doesn't want to be dissolved. It can break away from the forces of the things that are surrounding it to try to dissolve it. Give it more energy, it's even more likely to undissolve or to not be dissolved. Okay? Now, I do want you to read a page here. I'm going to force you to read here. 507, bottom of 507. What was that?
Is that 3 lines?
Yeah, and the next page.
Oh, okay.
Okay. Yeah, so, well, let's read this together. How about that? Somebody want to read for us, or at least start reading? We can popcorn around if you want.
Sure.
Go ahead, Ryan. You're a fast reader, way faster than me.
Everyday experiences of dissolving substances such as sugar may lead you to
think that solubility always increases in temperature. This is not the case. The dissolving of a solid occurs more rapidly at higher temperatures, but the amount of solid that can be dissolved may increase or decrease with increasing temperature. The effect of temperature on the solubility in water of several solids is shown in figure 11.6.
All right, stop for a second, just look at that figure.
Rectangle.
Okay. Typically, what are you seeing when you increase the temperature? What do you typically see with that graph?
Most water.
Increase in solubility except for a few things. Okay? Keep reading there, right?
Note that although the solubility of most solids in water increase with temperature, the solubilities of some substances, such as sodium sulfate and certain sulfate, serenium sulfate, cerium, cerium sulfate, decrease with increasing temperature. Predicting the temperature dependence of solubility is very difficult. For example, although there is some correlation between the sign of enthalpy of solution and the variation of solubility with temperature, important exceptions exist. Asterisk.
You want to go down and read again of that.
For more
In
information,
Chem Ed, you by all means go for it.
for more information, see RS.
Okay, keep going. Keep going.
The only sure way to determine the temperature dependence of a solid's solubility is by experiment. The behavior of gases dissolving in water appears less complex. The solubility of a gas in water typically decreases with increasing temperature, as is shown for several cases in figure 11.7.
Which, as you look at figure 11.7, all those guys are.
Even helium go down slightly.
I wonder if the size of the molecule plays an important role in. Looks like
Well, no, because oxygen,
oxygen's bigger than nitrogen.
but carbon monoxide would be bigger than oxygen.
Yeah.
It's carbon and oxygen.
There's probably some structural impacts too here. Okay, keep going.
What's out? This temperature effect has important environmental implications because of the widespread use of water from lakes and rivers for industrial cooling. After being used, the water is returned to its natural source at a higher than ambient temperature. Thermal pollution has occurred. Because it is warmer, this water contains less than the normal concentration of oxygen and is also less dense. It tends to float on the colder water below, thus blocking normal oxygen absorption. This effect can be especially important in deep lakes. The warm upper layer can seriously decrease the amount of oxygen available to aquatic life in the deeper layers of the lake. The decreasing solubility of gases with increasing temperature is also responsible for the formation of boiler scales. As we
You can stop. You can stop. I don't think we need to go through the rest of that. Have you ever heard of the thermocline? No. Okay, it's a big fishing term. That's why I know it. It happens in deeper lakes where typically your typical predatory fish that you would fish for, like bass and things like that, they cannot go deeper than a certain point because at the deeper levels there's so little oxygen because it's hotter at the top and cooler at the bottom. And so that's why, although as a fisherman people will say you're not a good fisherman if you're fishing deeper than the thermocline because you're not going to catch any fish down there. There just isn't any fish down there because there isn't enough oxygen to sustain life.
would there be different kinds of fish though, or not?
Yeah, probably not. Not your fish you would actually want to fish for.
Or wouldn't have enough meat on them, you say?